Okay, data analysis question. These are always a bit tricky because invariably they're about stuff that you won't necessarily have done. So the coefficient, a negative temperature coefficient thermistor with temperature is something you probably haven't come across before. But the moment it says negative, we should think about that. And if you look at the gradient of the graph, although it's changing, you can see that generally it's a negative type gradient. Let's have a look. So first of all, draw the best line of fit for the data points. So what I've done is I've tried to draw a line there, trying to go through all the points as best I could. I've started at the first point here, finished here. I haven't extrapolated the line because, to be honest, you don't know exactly what's going to go on beyond those points. You can have a guess, but we don't know. So I think it should go from point to point here as close as possible. 1 mark, a nice easy mark to get. All right, next. Calculate the gradient of the graph when temperature equals 291 K. All right. Well, as we said, the gradient is constantly changing. So what have I done here? I've gone on the temperature axis and gone up from 290 to 291. Careful on the axis here. How is it laid out? Well, we've got 290, 295. So it is definitely 291 here. I've then tried to take a straight line and made it as long as possible to try and get the gradient, but also tried to keep the numbers fairly straightforward as well. So I've taken it from here 7.4 here down to 1 here, just to keep the numbers simple. So in terms of finding the gradients, what have we got? We've got 7.4 minus 1, and we've got 312, which is the endpoint here, minus 280, which is here. And so that gives us 6.4 over 32, and it's 0.20. It's negative gradient, so it's minus 0.20. Why two significant figures? Well, let's have a look. What have we been able to do? In terms of the resistance, we haven't been able to use a value more than 2 significant figures. Yes, 3 significant figures for temperature, but it's 2 significant figures for resistance, so the least number of significant figures is the answer. So 0.20, i.e. 2 sig figs. And that's 3 marks for that part of the question. State the unit for your answer. Well, what did we do? We did rise over run, so we did ohms divided by Kelvin, so it must be ohms Kelvin to the minus 1. So the answer is ohms Kelvin to the minus 1. And a nice easy mark there. Part C, the uncertainty of the resistance value is 5%. The uncertainty of the temperature is negligible. So we're only worried about the uncertainty for the resistance. And on the graph, draw error bars for the data points at temperatures 283K and for the data point to temperature equals 319. Seems an awful lot of work for 2 marks, to be honest, but let's have a go. Resistance error bars, what have we got? 7.5 ohms plus or minus 5%. So let's see what 5% is. 5% works out at 0.375. So our positive value is going to come out at 7.88, which is roughly 7.9. And our negative value is 7.12, approximately 7.1. So we're taking an error bar for the temperature at 283K. Is that correct? 7.5 ohms, yep. So at 2.283K, we're taking an error bar here, which is going from 7.9, which is here, correct? Well, it's more like there, 7.9, and we're going down to 7.12, which is about 7.1, and we said that's 7, so 7.1 must be about here. So our error bar, drawn with a ruler, not in this case, is from there to there. Second one, 1.9 ohms plus or minus 5%. That's going to give us a positive value of 2.9 and a negative value of 0.9, and that is for our second reading, which is 300 and, let me see, just double check, 1.9 ohms, yes. So that's going to go from 2.9 to 0.9. So we go from 2.9 to 0.9 on 1.9 ohms. Where's our 1.9 ohms value? it's for 319K, so it's this one here. So 2.9 is going to take us to, that's 3, so it's going to take us to about there. And 0.9 is going to come down here. Well, we've said that's 1 here, so 0.9 is just below it, and that's a much longer error bar. Whoops, and that should have been drawn with a ruler through there. Okay, so that's like variable. As I said, an awful lot of work for 2 marks. Personally, if you're in a rush, I wouldn't have spent too much time on it. Okay, next, the electric current through the thermistor is 0.78 milliamps. The uncertainty electric current is 0.01 milliamp. Okay. Calculate the power dissipated by the thermistor at temperatures 283K. We're not worried about the uncertainty at this stage. We just want straight values for the 1 mark. In other words, we're going to use the formula I squared R for power. Multiply the current value. Be careful, it's 0.78 milliamps, so it's 0.78 times 10 to the minus 3. Remember, it's squared because it's I squared, times the resistance, which is 7.5. And on your calculator, that's going to give you 4.5 times 10 to the 6 or 4.6 times 10 to the 6 watts. 1 mark, straight value. Determine the uncertainty in the power dissipated by the thermistor at temperature 283K. What are we going to do now? Okay, we need the uncertainty in I squared, and we also need the uncertainty in R. Well, the uncertainty in I squared, we've been told, is plus or minus 0.01 milliamps. That's given to us there. So that's going to give us, because we're careful, it's I squared, so 2 times 0.01 over 0.78, which gives us 2.6%. Uncertainty in R from previous part of the question was given to us as 5%. Here we go. So we've got a total uncertainty of 5% plus 2.6%, which is a total of 7.6%. What are we going to do then? We take that 7.6%, take the value we just calculated in terms of the power, and what do? We get an uncertainty of either, depending on the value that you got here, of 0.35 times 10 to the minus 6 watts, or 0.35. I think the other one that comes out is 0.36 times 10 to the minus 6 watts. So either value will be accepted. Notice here we only have 0.01 milliamps in terms of the uncertainty. That's 1 sig fig. So therefore the answer should be to 1 sig fig. Thank you very much.